Design of Rpfc for power quality improvement in railway power system using fuzzy logic controller. Abstract: this paper is to create power quality in electric railway systems with the assistance of fuzzy logic controller. Concentrating on the cargo prevailing electrical railroad power system, ERPS, blended with air conditioning DC and air conditioning DC air conditioning trains, its power factor 0.70, 0.84. This paper proposes a power factor situated railroad power flow controller, Rpfc, for the power quality improvement of ERPS. In this paper the thorough relationship of the primary power factor, converter limit, and the two-phase load currents are introduced. By this technique we can likewise control the power flow trade between the grid and the load, with the goal that instantaneous active and reactive power is maintained constant. Moreover, as the main commitment of this paper, the ideal remunerating procedure suited the irregular varied two-phase loads is broke down and planned based on a genuine footing substation, for the reasons for fulfilling the power quality standard, improving Rpfc's control adaptability, and diminishing converters' ability. Here we are utilizing the fuzzy controller contrasted with different controllers, i.e. the fuzzy controller is the most reasonable for the human basic leadership component, giving the operation of an electronic system with choices of specialists. What's more, utilizing the fuzzy controller for a nonlinear system takes into account a decrease of indeterminate impacts in the system control and enhances the effectiveness. By utilizing simulation results we can examine the improvement of the power quality in electric railroad systems utilizing fuzzy logic controller. Index terms: power factor, negative sequence, power quality, power flow controller, electrical railway power system, converter, fuzzy logic controller. Introduction. Power quality has become an increasing concern in railway systems. Poor power quality affects the performance, reliability of the railway system as well as having an effect on equipment attached to the local distribution network. The analysis of power quality on a rail system is essential, to enable the analysis of train performance and to assess the effects of a rail system on the adjacent distribution network. Railway systems are electrically complex. The loads, trains, are constantly moving and their electrical behavior is constantly changing. Modeling is an ideal tool to analyze the power quality of such a complex system. An ideal model would be accurate yet computationally efficient. As the popular PQ improvement rig, static VAR compensator, SVC, 9, 10, static synchronous compensator, STATCOM, 11-15, active filter 16-21, transformer integrated power conditioner 22-24, railway power flow controller, Rpfc, 5, 25-30, and the well-designed train-mounted front-end rectifier 31-33 are commonly used in ERPS. Considering the comprehensive performance, Rpfc is concerned greatly by related departments due to its compatibility. It can, unlike the above rigs, integrate in the secondary side of almost all kinds of traction transformer. By rebalancing the two-phase active power, and compensating the reactive power or harmonics in each phase independently, RPF can deal with almost all the main PQ problems of ERPS. Additionally, the feeder voltage stability and the capacity utilization ratio of the main transformer can also be enhanced significantly 26-30, which are attractive for improving ERPS's transport capacity and cost efficiency. Power quality has to be considered from two perspectives, the railway system and the local distribution network to which it is attached. Poor power quality on the railway system affects performance, limits capacity and may introduce a need for additional maintenance. Distribution. Network operators stipulate power quality standards. Railway systems are required to meet these standards. Power quality is divided into categories. 1. Railway systems typically suffer from poor voltage regulation and harmonic distortion. Voltage regulation affects the performance of traction units and imposes a capacity limit on the system. Harmonic distortion can cause damage to traction units, particularly motors too. Rail systems can cause harmonic distortion and voltage unbalance on the local distribution network. The harmonic distortion is caused by the nonlinear currents drawn by the railway system and in DC systems by rectifying substations. Voltage unbalance is present in AC systems, where the rail system draws large currents from a single phase of the supply. To additionally enhance Rpfc's ability, usage capacity and control adaptability in both outlining and working stages in cargo prepare overwhelming ERPS, in this paper, we will center around the arrangement of the accompanying perspectives. 1. Establishing the connection between the primary PF with Rpfc's remunerating limit, the converter's ability can be adaptably composed by modifying the primary PF. 2. In the commence of limiting Rpfc's ability for a given PF, considering an ideal control system to diminishing NSC and NSV in a satisfactory level. 3. The proposed control procedure ought not exclusively be connected in the basic single-phase ERPS, yet in addition in the vital regular utilized two-phase system, see Fig.1. This paper is sorted out as takes after. The mathematical model of the Rpfc coordinated two-phase ERPS is displayed in Section 2. In the introduce of relief NSC, as the main commitment of this paper, Section 3 gives the PF-situated ideal phase system for Rpfc. Simulation are given in Section 4 and V segment 6 is the conclusion, where PLA and PLSS are the load's active power in phase A and SS. It can be seen from 12, in light of the fact that .A, SS can be pre-acquired for a specific sort of a transformer, example the V/V transformer and other sort of the adjust transformers 35, 36, A and SS are just dictated by PFA PFC or FA FCC, 10, and 2. Henceforth, the active and reactive power of the Rpfc can be adaptably balanced by controlling the primary three-phase power factors, if the PFS of the two-phase loads are pre-ascertained CFLA and FLSS in 12, which will be talked about later on. ICOMPENSATINGISTRATEGYIDESIGN. The possible compensating scheme. For the consideration of planning accommodation and the necessity of PF equals 0.9, we let from 13, 17, and Table I, the relationship of IUND and PF asterisk of Model 1.5 are shown in Fig 4 and Fig 3, A. We can observe that however the limit surfaces of Model 3 and 5 are close Fig 3, A, the NSC stifling capacity of Model 3 is superior to that of Model 5, Fig 4. It demonstrates that, if Model 5 is substituted by Model 3, Rpfc can show signs of improvement. NSC stifling capacity with nearly has a similar VA limit of Model 5. In other words, the remunerating procedure joint of Model 2, 4, and 3 has higher exhaustive execution than the one consolidated by Model 2, 4, and 5. So the certified OCS ought to be adjusted from Fig 3, B, into Fig 5, and its determination is given in 18.I. OCS, asterisk equals 0.95 Model 3, 0 MW equals 0.415. Model 4, 0.55. Equals 1.67. Model 2, 1.67. Equals 8 MW, 17. Fig 6 gives the slants of line OA and OB, i.e., COA and COB in various PF asterisk. Note, OA and OB are the limits of the three remuneration demonstrate appeared in Fig 5, the loads PF are as yet affirmed to be 0.8, on the grounds that the power factor changes in a little rang around 0.8 in the deliberate substation. It can be observed from Fig 6 that, COA's change amplitude is 0.114, while, it fluctuates in generally expansive range for COB. For execution of the proposed OCS, a satisfactory execution can likewise be acquired by settling KOA on 0.5, and modifying COB by PF asterisk concurring. The blue band appeared in Fig 6. It can be pre-implanted in the advanced controller's memory space in useful application. Fig 7 gives the two-phase loads distribution graph of a genuine V/V transformer-based footing substation, see Table 2. The measurement results of Fig 7 demonstrate that right around 95.2% of the load points are situated in the rectangle zone of CEDO, where the likelihood of the points distributed in .ACO and .ABO, or .of10, or .of20, is around 85%. Besides, we can likewise locate that, surpassing half of the load points are situated at stake OC and OD. Take note of, a few points are covered on these two lines, which means the V/V transformer's ability usage ratio can be additionally improved in a vast potential. Based on the above measurement results, our consideration ought to be centered around the loads situated in CEDO and its limits. Fig 7. The two-phase loads distribution of a real V/V transformer-based traction substation. The surface of S, versus PLA and PLSS, inside rectangle region of CEDO appeared in Fig 7, can be gotten based on 20, and the SD given in Table II, which is appeared in Fig 8. From the state of the surfaces appeared in Fig 8, it can be reasoned that the maximum S, of Model 3, 2, and 4, happens on the point A, B, and E for any given PF asterisk, individually. The surface of S, versus PLA and PLSS, within rectangle area of CEDO shown in Fig 7, can be obtained based on 20, and the SD given in Table 2, which is shown in Fig 8. From the shape of the surfaces shown in Fig 8, it can be concluded that the maximum S, of model 3, 2, and 4, occurs on the point A, B, and E for any given PF*, respectively. Fig 8. The relationship of S with PLA and PLSS. Note, PF* equals 0.95. Fig 9 gives the relationship of the S in A, B, and E, i.e., the maximum S, S max, with PF* for this footing substation in Model 2-4. Clearly, this blocking capacity of Model 4 is greatly improved than that of Model 3 and 2, however the last S max diminishes when PF* turns out to be extensive. Fig 9 additionally demonstrates that the maximum negative sequence powers controlled by OSC are not as much as the authorization esteem 9.72 MVA, i.e., 486 MVA times 2%, which means the Chinese national standard can be fulfilled when PF* is set inside 0.9 to 0.99. It ought to be commented here is that, if the authorization line of S crosses with other maximums line of Model 2 or 3 appeared in Fig 9, the correct hand abscissa of that intersection point ought to be chosen as the important PF*, on the grounds that the left one will lead Vunp out of the utmost negative capacity with PF* in Model 2, 3, and 4. The capacity utilization capability of Rpfc should also be included in our concerning scope. From Fig 10, the maximum SRPFCs, i.e., SRPF max, reducing ratio decreases heavily when PF* 0.95. Note, the maximum SRPFC point in PLA PLSS panel, i.e., Fig 7, is labeled in Fig 10. Besides, Rpfc's designing capacity SRP designs decreasing ratio also shows relatively large value, 23.43%, when PF 0.9, 0.95, it increases when PF 0.9. Note, SRPF design equals 2 times max converter A, converter SS. This is because IGBT is a voltage-sensitive device and the DC link voltages of converter A and SS are the same. EA in Fig. Point 10 means the maximum converter capacity belongs to converter A located in point E. Considering cost efficiency, PF* can be selected from 0.9 to 0.95 for this traction substation. Ratio 1 maximum SRPFC/FCM based maximum. SRPFC and SRP designs reducing ratio 1. SRPF design/FCM based SRPF design with PF*. Under the control of OCS. Control strategy realization. The control system of the Rpfc is plotted in Fig 11. A few particulars ought to be made for it. The FFT strategy or the instantaneous reactive power theory 37 can be utilized for the estimation of the load's active and reactive power in the PQ block, while the relative resounding controller, PS, is received as the present controller for its grade. Following capacity in sync phase system. For the adjustment of VDC in the back system, rather than the figured PCA, the genuine PCA is produced by the DC link voltage pi controller in converter A. Furthermore, more consideration must be paid on the acknowledgement of the repaying power figuring block, and the accompanying 4 steps can help us to get the objective. 1. According the deliberate two-phase loads, example Fig 7, SD, and the exhibited slops of OA and OB appeared in Fig 6, the PF**s directing extent can be resolved for the motivations behind fulfilling the negative sequences standard, example Fig 9, and having generally little limit, example Fig 10. 2. Based on the preset PF**, example PF**. 0.9, 0.95, the inclines of OA and OB can be resolved from Fig 6. The remunerating model of OCS can be controlled by the load points area in the load distribution panel appeared in Fig 5 or 7, which can be reasoned by distinguishing. 4. If the repaying model is gotten from step 3, Fa, FB, and FC can be figured from table I and 13, so as A and SSC, 10. Consequently, the repaying active and reactive power of Rpfc can be at long last gotten from 12, note, in 12. FLA equals arctan, QLA/PLA, FLSS equals arctan, QLSS/PLSS. 4. Fuzzy logic controller. In FLC, basic control action is determined by a set of linguistic rules. These rules are determined by the system. Since numerical variables are converted into linguistic variables, mathematical modeling of the system is not required in FC. The FLC comprises of three parts: fuzzification, interference engine, and defuzzification. The FC is characterized as I7 fuzzy sets for each input and output. 2 triangular membership functions for simplicity. 3 fuzzification using continuous universe of discourse. 4 implication using Momdani's, min operator. V defuzzification using the height method. Fuzzification, membership function values are assigned to the linguistic variables, using 7 fuzzy subsets: NB, negative big, NM, negative medium, NS, negative small, Z, 0, PS, positive small, PM, positive medium, and PB, positive big. The partition of fuzzy subsets and the shape of membership CE, K, E, K, function adapt the shape up to appropriate system. The value of input error and change in error are normalized by an input scaling factor. Defuzzification, as a plant usually requires a non-fuzzy value of control, a defuzzification stage is needed. To compute the output of the FLC height method is used, and the FLC output modifies the control output. Further, the output of FLC controls the switch in the inverter. In UPQC, the active power, reactive power, terminal voltage of the line and capacitor voltage are required to be maintained. In order to control these parameters, they are sensed and compared with the reference values. To achieve this, the membership functions of FC are error, change in error, and output. The set of FC rules are derived from U equals -AE plus 1A *C 24, where A is self-adjustable factor which can regulate the whole operation. E is the error of the system, C is the change in error, and U is the control variable. A large value of error E indicates that given system is not in the balanced state. If the system is unbalanced, the controller should enlarge its control variables to balance the system as early as possible. On the other hand, small value of the error E indicates that the system is near to balanced state. B. The waveforms represents the primary three-phase currents, power factor, voltage, and current unbalance ratio, capacity of Rpfc when it is driving variable load with constant power factor. It demonstrates the three-phase load changes such that the primary PF move along PF *WTH the satisfactory execution. Also, IA, IB, and IC have a tendency to be the adjusted three-phase currents when PF** wound up bigger. The waveforms in the condition of variable PF* with constant load. Fig 5.7 represents the primary three-phase currents. Fig 5.8 represents the PF* and PF. Fig 5.9 represents the voltages and currents unbalanced ratio. Fig 5.10 represents the capacity of Rpfc. Case 2, fuzzy controller. A. The waveforms represent such that the primary three-phase currents, power factor, voltage, and current unbalance ratio, capacity of Rpfc when it is driving a constant load with variable power factor of a fuzzy-based controller. It demonstrates the three-phase load changes such that the primary PF move along PF* with the satisfactory execution. Also, IA, IB, and IC have a tendency to be the adjusted three-phase currents when PF* wound up bigger. The waveforms in the condition of variable PF* with constant load. Fig 5.11 represents the primary three-phase currents. Fig 5.12 represents the PF* and PF. Fig 5.13 represents the voltages and currents unbalanced ratio. Fig 5.14 represents the capacity of Rpfc. B. The waveforms represent such that the primary three-phase currents, power factor, voltage, and current unbalance ratio, capacity of Rpfc when it is driving a variable load with constant power factor of a fuzzy-based controller. It demonstrates the three-phase load changes such that the primary PF move along PF** WTH the satisfactory execution. Also, IA, IB, and IC have a tendency to be the adjusted three-phase currents when PF* wound up bigger. The waveforms in the condition of variable PF* with constant load. Fig 5.15 represents the primary three-phase currents. Fig 5.16 represents the PF* and PF. Fig 5.17 represents the voltages and currents unbalanced ratio. Fig. 6 Conclusion. This paper proposed a power factor arranged Rpfc for the power quality improvement with both pi and fuzzy controller. The mathematical model of the Rpfc coordinated ERPS and the far-reaching plan technique for the proposed control methodology are given in detail, based on a genuine footing substation. The simulation and the exploratory results confirm the accuracy of the proposed considers. In the start of fulfilling the norms of the reactive power and NSV, this paper gives an ideal control technique for the PQ improvement, control adaptability upgrade, and the lessening of Rpfc's remunerating and planning limit in two or single-phase Rpfc incorporated ERPS. In other words, this control technique can influence the system to have an attractive high cost effectiveness in two or single-phase footing load conditions.